Hi, in today's tutorial we are going to classify more than 500 types of birds. So we will use the Inception version 3 model. We will do a transfer and fine-tuning for this model and adapt it to our needs. So basically we will have two Python codes. One will be importing the data and building the model using transfer learning techniques, and the other Python program would be testing our model. So first of all, this is our dataset from Kaggle. As you can see, it's already organized with the train, validation, and test. I will choose some of the categories. In each one of them, there are several hundreds of images of those birds, and we will download this dataset locally and start coding. As always, I will leave a link for the dataset and also a link for the code as well. As you can see, those are all the images already downloaded and are locally at my machine, and we will start with the coding. First of all, we will import the relevant Python libraries. Next, let's initialize dataset path, and this line will set the path for the directories containing the dataset. We have to change the direction of the slashes on Windows, of course. Next, let's define the train path, the validation path, and the test path as well. As you saw earlier, the data is already organized within these folder names. Now let's see how many classes we have on those folders. So this code counts the number of classes in the dataset. It does it by listing all the folders, the directory within the train directory, and then counting the numbers of items in the resulting list. As you can see, the number is 525. Now let's load one image. In order to do that, we will use the pyplot library, and we would like to view a random image. So we will create a function for that, and this function is defined to display a random image from a specific class within a target directory, and it randomly selects an image file from a specific directory and display it using the matplotlib. So this is the target of this function. Let's wait a few more seconds for finish the coding. Let's read the image from the target folder. We will use the ImShow to display the image. Let's add the title for the image with the target class. We know don't need axis, it's not a diagram. And let's print also the shape of this image. Now let's run the function with the train path, and let's choose one of the categories. Let's choose one of it randomly. Okay, this one, Victoria crowned pigeon. So this function will choose randomly one of the images inside this specific folder. Nice. This is one of the images. Let's run it again. We will show a different one. Nice. Okay, that works. And let's continue to the next step, which is building the model. And before building the model, we need to arrange the data or import the data to the relevant variables that will be used by the model. So we will set up a data generators for that, and data generators are initialized for the training, testing and validation dataset, and these generators help us loading and pre-processing the data efficiency. So we will rescale the images, so every pixel has a value between 0 and 255, and we should normalize the data between 0 and 1. So we will divide all the images on the train, test and validation between 0 and 1. We will divide the values by 255. In the next step, we will use these data generators. So first of all, let's load the train data. In order to load the train data, we will use the train generator, and we will use also the function flow from directory. This function gets several arguments. The first argument is the path for all the train images. Then the batch size. Batch size means how many images will be stored in each batch. Next is the target size, and the Inception V3 model requires the 224 by 224, and of course the class mode will be categorical since we have more than one category. And we will do the same for the test and the validation as well. And let's finally fix the name of the path, and I believe that the word directory should be fixed as well. So let's wait a few more seconds. Now let's fix the directory, and I believe that's it. Okay, let's run it. As you can see, these are the amounts of images in the train, test and validation. Cool. Now let's create our model. So we will use, as I mentioned earlier, the Inception V3 model, and it's used as our base model for the transfer learning. And the base model layers are frozen to retain their learned feature during training. We will use the existing weights of this model, and we will add our own layers to the existing model. We will use a global average pooling layer. It will be added to reduce the spatial dimension of the feature maps. And we will use, of course, a dense layer, and we will define our own number of classes, which is 525 classes with softmax as activation function. So now let's wait a few more seconds for adding those layers to the existing Inception model. So the X variable will be our model. We will add each time another layer to this X model. Now we are adding the average pooling layer. As you can see, the X has the base model, and now we are creating a new layer named global average, and by the end of this command we are adding the X base model. So each time the shape will include the last layer that we have added. Now let's add the last layer, which is our dense layer with the 525 classes. The same as before, we are adding a dense layer, number of classes, and softmasks as activation function, and we are adding the X as the last command. Okay, now let's merge the input base with the output layers that we have created. So the model variable will include both of the input and the output. The next phase will be compiling our model. So we will use a categorical cross entropy as our loss, and the optimizer will be Adam optimizer. Let's add a high learning rate of a value of I believe 0.01. It should do the job, and the metrics will be accuracy. Now let's print the summary of the model just to double check that everything is okay. Now after running this code, you should focus on two issues. One is the number of classes, which we are expecting to see 525, and the other one, we are going to train only 1 million parameters. All the rest is non-trainable, so model should run very quickly. Now we will define number of epochs as 30, but basically, as you will see next, we are going to define callbacks, and in these callbacks we will stop the training if we will not see any improvement. So as you can see, we are importing three functions: model checkpoints, reduce of plateau, and early stopping. And basically in these functions we are going to follow the training and examine several variables. First of all, model checkpoints checks if there was improvement during the training, and each time that the model was improved, the training was better from before, it will save the weights with the best model files. As you can see, we defined it earlier as 525bird.h5. Next, we will let's say examine the value accuracy, and if it was not changed during 4 epochs, we will change the learning rate on a specific factor. Factor is the how many percentage we should change it. And then the early stopping, we will wait 5 training epochs, and if there was not any improvement during 5 training, the model will stop. And that's why we are not going to wait 30 epochs. Now it's the next step is the training. We will use the Feit function. As you can see, a very straightforward process. We are sending several arguments as the train data, how many epochs, how many steps per epochs, and also the validation data, so we can validate the new data during the training. Let's also define the validation steps. And at last, we will add our callbacks, our three, let's call it parameter functions that investigates the training and get decision if to stop training, if changing the learning rate, as I mentioned before. Okay, let's finish coding, and the next step will be validation our test data, the one that the validation never saw before. So this slide will evaluate the trained model performance on the test data, and it will print out the loss and the accuracy matrix on the test dataset. Finally, we are in the last step. After the training process, we would like to visualize our lost curves. So we will create a function. Let's call it plot lost curves. And this function plots the training and the validation lost curves over the epochs. So basically you're creating a diagram that display the accuracy and the loss. And this also provides insights into the model training progress, and it will help us to visualize how well the model is learning from the data and whether it's overfitting or underfitting. So now we will define more of the display values in our diagram using the PLT object. So one of the lines will be the training lost and one will be the validation lost. Let's choose a title for that, and let's define who will be the X label, which this is the over time. That is the epochs basically. And let's copy the process for the accuracy as well. Let's wait a few more seconds to finish the coding. Okay, the accuracy is done as well. Now we have to run the function, and we will send the results from the Feit process. Or I have to fix I have a syntax error in the name, so let's fix it. It should be accuracy. Okay, that's okay. And the show function will display both diagrams, and we are ready to run it. Okay, let's wait for the start of the training. Okay, this is epoch number 1. Let's wait a few more seconds just to see that the training process is okay. As you can see, the valve accuracy was improved, so there was a new copy of the weights that was saved in our file. Also, after epoch number 2, you can see that there is an improvement from 0.7 to 0.74. Let's see the fourth one. Another improvement. Great. So each time we are getting an improvement, we are saving the model, and as you can see now, the value accuracy was not improved. So the model keeps the last one, the best one is being saved each time. Now we are heading to 0.8. So the model runs very, very good. And let's jump directly to the endpoint. As you can see, our model is 0.91, and this is the loss and this is the accuracy. Very good results. So now let's test our model with a fresh and a new image. So let's create another Python file. Let's call it step number 2, and it would be testing our model. So first of all, we are going to import some libraries, TensorFlow, OpenCV, and some necessary modules from the Keras. These libraries will be used for image processing, loading our model, and performing the predictions. Now let's define some constants like the image size, which is 224, and also let's define the path for the dataset and training directory. All this will be initialized, and we will copy it from our previous code. Let's copy it's basically the same starting point of the code, and this will help us for two things. One, to define number of classes, and more important, we will create a list that contains all the classes names, and then when we will get the class ID from the prediction, we will extract the class name. Now we should load our saved model. We will use the function load underscore model in order to load our saved model. And let's print our model by printing the summary, and this will help us to figure out if the model was loaded successfully. We're expecting to see the 500 classes, as you can see as the last row. So the model was loaded and we are ready to run the prediction. But before that, we have to convert our fresh new image. So let's create another function. Let's call it prepare image, and we will send as argument the path for the location for the image, and we will pre-process the input image before making the prediction. So we will load the image, we will resize it to our target size, and we will convert it to an array, and then we will expand the dimensions and normalize all the pixels value. This will make our image ready for prediction. Great. Now let's grab a test image. So we have to define the path for the test images. We can copy it from our previous code. So as you can see, we are choosing one of those folders. Let's choose an albatross folder. So we will try to predict albatross image. From the test image, we will choose an image named 4.jpg. Now we will use OpenCV in order to read the test image from our specific file and store it in our variable img. Now we will run our function, the prepare image, and we will get the result into an img4 model. This basically preparing our image for prediction. Now we will run the predict function, and this function used to obtain predictions on the pre-processed image, and the result basically has more than 500 values. So we will get the highest values using the argmax function. Now the answer will include the category number out of 525 categories. So basically the value is 9. That means that this albatross image is category 9. So let's define the text or extract the category name. In order to do that, we will use the classes list, and we will check which text is under this index. In our case is index number 9. So let's run it again, and as you can see, the predicted class is albatross. Great. So now let's add another function. We will use the putText function in order to put the text on our image. So we would like to display this text on the image. So this function overlays used to overlay the predicted class label on the original test image, and the modified image will be displayed using the imShow function. So now we are defining the font, the position of the text, the thickness of the text, a very common practice using the putText function. And now we are ready to run once again the prediction, and we are expecting to see the image with the text class. Great, as you can see, this is the albatross image. Now let's try another image. Let's choose another class. a random class. I don't know what is Anhinga, but let's choose this one. So let's create another test image as Anhinga, and let's choose another image. Let's call it image. Let's choose image number 5. And this is the prediction. Very nice. Thank you very much. I hope you enjoyed this tutorial. You are most welcome to subscribe my channel. Bye bye.